Okay, I'll get started. Just want to begin with a final reminder about Test 2. I hope it's a reminder about Test 2. Test 2 is on Thursday, exactly the same format, true-false questions and fully worked out problems as Test 1. There's a practice test online on Canvas with and without solutions. You went through, I think, the practice test in Monday's recitation. The content is all the content since Test 1, so it's this list of content, this list of lectures since Test 1. I had a couple of questions about whether Kirchhoff's rules are on this test. They're not on this test because that was really Test 1. That was covered in lectures before Test 1. So it's these topics. It's magnetism and it's electromagnetism. It's the laws of magnetism and laws of induction and the material we do today. Any questions on all of that? Okay, sounds like we're all good about Test 1, 2. Today's class is all about the joining together of electricity and magnetism and the prediction of an electromagnetic phenomena, light. So it's all about the unification of electromagnetism and the prediction of light waves. Specifically, I want us to begin by uncovering the connections between electricity and magnetism, and thereby joining together, unifying electricity and magnetism into what we call, big word, electromagnetism. So that'll be the first bullet. Second bullet is we'll uncover that electromagnetism predicts the existence of an electromagnetic wave that is built out of electric and magnetic fields that sustain themselves and propagate themselves through space and time. So we'll discover electromagnetic waves, and that's the second bullet here. Third bullet is that we'll look at some properties of electromagnetic waves. We'll look at properties like the speed that electromagnetic waves travel at, things like the energy that electromagnetic waves carry, the momentum that electromagnetic waves carry, the electric and magnetic fields within the electromagnetic waves. So all these sorts of properties we'll discuss in today's class. A classic example of electromagnetic waves is a sunny day today. This is Sunlight Special today. Sunlight is an electromagnetic wave, and it wasn't to the unification, the joining together of electricity and magnetism, that the nature of sunlight, the working of sunlight was understood. Okay. And sunlight's important, right? Sunlight is why we're alive. Sunlight is the reason that we've got things to eat, and sunlight keeps everything alive on Earth. Okay, so just to stress again, within physics, the material in this class was a big deal because it's the second great unification. The first great unification was the unification by Isaac Newton of celestial and terrestrial motion through gravity. And then the second great unification is due to James Clerk Maxwell. It's the unification of electricity and magnetism and the understanding of things like sunlight. So it was a big deal, I guess. Okay, so if you want somebody to blame for this class, you go blame James Clerk Maxwell. He was the single-handedly, he was the person that joined together electricity and magnetism into electromagnetism. He single-handedly was the person that realized that when you join together electricity and magnetism into electromagnetism, you predict an electromagnetic wave. He single-handedly, in one evening, realized the nature of light. The nature of sunlight, or all forms of light, was sunlight. Other light is an electromagnetic wave. So it's a huge, huge achievement. I got two slides here that basically describe evidence that electricity and magnetism are connected. The first slide is evidence that electricity and magnetism are connected in a very obvious way that you already know. The second slide is that electricity and magnetism are connected in a somewhat less obvious way, and a somewhat hidden, sort of secret way. We'll put those two connections together like Maxwell put those two connections together, and that will lead us to the complete electromagnetic theory, the complete theory of electromagnetism. That's the third slide. That's the slide that predicts sunlight. And then we'll start working on the prediction of sunlight and other forms of light. Okay, so this slide here is a completely obvious link between electricity and magnetism. There is a completely obvious link between electricity and magnetism. It wasn't known for thousands of years, but it became apparent once it was realized that electricity arises from charges and magnetism arises from currents, which are moving charges. So one obvious link between electricity and magnetism is that charges are the source of electric forces. Electricity is a force that's between electrical charges. And magnetism, well, that's a force between also electric charges. And electric charges also give rise to magnetism. So at the root of electricity, at the root of magnetism is the same property of nature. What generates electricity, electrical forces, what generates magnetism, magnetic forces, is the same property, is the same characteristic of nature. It's electric charge. And so that's an obvious, huge clue that electricity and magnetism are related to one another. Now, we discovered this clue that electricity and magnetism are related to one another from what I would call a kind of frozen world of electricity and magnetism. Frozen world of electricity and magnetism, I mean that when we talked about electricity, we just talked about static arrangements of charges, stationary arrangements of charges, and stationary or static electrical fields. And we saw how charge was responsible for those electrical fields. When we talked about magnetism, we talked about steady currents, just currents constantly flowing, a steady currents, and how those currents, those moving charges, create magnetic fields. So we discovered this link through kind of steady currents, stationary charges, a frozen, unchanging world. This is the non-obvious link between electricity and magnetism, and it's the last few lectures that underneath those last few lectures, there is a non-obvious link between electricity and magnetism, or a less clear link between electricity and magnetism, and it's related to induction. So, when we talked about electricity, we first introduced Coulomb's law, which is a force between charges, but it felt a little empty in a way because there was no explanation of how that force was transmitted, how that force was carried, until we introduced electrical fields as mediating the forces. So it felt a little better then. Similarly, we could have introduced magnetism as a force between electrical currents. Like currents attract, opposite currents repel, but that would have been a little bit empty. if we hadn't talked about the magnetic field that's carrying or mediating the magnetic forces between electrical currents. So with Coulomb's law, the law for the force between charges, there comes a deeper understanding when you understand that it's fields that carry the electric fields carrying the forces between the charges. And with Ampere's law, the force between electrical currents, there comes a deeper understanding when you understand that magnetic fields carry those forces. The same thing with induction. When we talked about induction, when we talked about Faraday's induction, we talked about induced currents, we talked about induced EMFs, we have a law that describes induction, Faraday's law of induction, that the rate of change of flux determines the induced electromotive force and induced currents. But why? Why does the rate of change of flux induce electromotive forces and induce currents? Why is that? There's no explanation of the why, like we started with no explanation of why there's electrical forces and said there was electrical fields, and then what's the explanation of forces, magnetic forces between currents? That's magnetic fields. So why is there induction? Why does induction exist? James Clerk Maxwell realized that induction exists because when you have a world that isn't a frozen world of stationary charges, a frozen world of steady currents, but rather your charges move around, your currents change, in that world where you've got changing, time-varying electrical fields, time-varying, changing magnetic fields, the electric and magnetic fields actually interact with one another and generate one another. And this is a whole new world that's sort of the bedrock of induction. It's the reason that there is induction. So in James Clerk Maxwell's theory, the reason for the induction that we've looked at is that when you have a time-varying magnetic field, here's a picture, the green lines are meant to be the magnetic field lines. They're meant to be changing, they're getting stronger, or they're getting weaker, or they're changing their direction. So this is a time-varying magnetic field. It's denoted by delta B over delta T not being zero. So it's changing in some way. That creates loops of electrical field. And that's what causes the induced EMFs. That's what causes the induced currents. It's those loops of electrical field. So this is a deeper understanding. This is a field-like understanding of the law of induction. Just like we had a field-like understanding of electricity, a field-like understanding of magnetism, now we've got a field-like understanding of induction. It's the fact that time-varying magnetic fields create electrical fields. So this explains for example, transformer induction, when two circuits talk to one another, when your iPhone talks to another iPhone. Along with that, James Clerk Maxwell also introduced a sort of mirror effect. The mirror effect is if you have an electrical field, and that changes in some way, so maybe this electrical field here is the orange field lines. Maybe it's getting stronger with time, or maybe it's getting weaker in time, or maybe it's changing its direction. They're all changes in the electrical field. If this is a time-varying electrical field denoted, delta E over delta T, the change in the electrical field is not equal to zero, then that creates a magnetic field. It actually creates loops of magnetic field here. So it's pictured here. This is a new phenomenon, but it's a real phenomenon, and actually, when you charge up a capacitor, you discharge a capacitor, so that's changing electrical field. At those moments, at those instants, there's actually magnetic fields too. So this is a real effect beneath magnetic fields that appear during charging and discharging of capacitors. Okay, so this is Maxwell's new idea, that underneath induction, beneath induction there's an explanation in terms of electric and magnetic fields. And the explanation is really in that electric and magnetic fields, when they change in time, they interact with one another. A changing magnetic field will create an electrical field. A changing electrical field will create a magnetic field. That's some connection, some interaction between the fields themselves. That was completely absent with our static charges and our steady currents, where we had time not changing electric fields and magnetic fields. So this is really a new thing. So this is the second link between electricity and magnetism. The first link was that that both ultimately, both electricity and magnetism are caused by, generated by a property in nature called charge, electric charge. The second link is that the fields, the electric fields, magnetic fields that are responsible for the magnetic and electrical forces, they interact with one another when they change in time. They're not separate, isolated from one another. They literally talk to one another, communicate with one another when they vary in time. So that's the second big link. Maxwell put this all together into a complete theory of electromagnetism. And this is the complete theory of electromagnetism that predicts light. And this one slide here is a representation of his complete theory of electromagnetism. The whole theory of electromagnetism I've just put on one slide. The whole theory of electromagnetism says that there are actually 4 sources of electric and magnetic fields. The 4 sources of electric and magnetic fields are the 4 cartoons in this overhead. The 2 top sources of electromagnetic field are, well, charge is a source of electrical field, that's this top left here, and moving charge is a source of magnetic field, that's this top right picture here. So those are 2 well-known to us already, sources of electric and magnetic fields. The 2 new sources of electric and magnetic fields are when electric and magnetic fields themselves vary or change with time. Those are the 2 bottom pictures here that I just introduced. If you have a time-varying magnetic field, it creates an electric field. If you have a time-varying electrical field, it creates a magnetic field. So these 4 pictures, you can go home tonight and you can call mum and you can say, I know the complete theory of electromagnetism. I know the 4 ways that you can make an electrical magnetic field. You can make it with charges and moving charges. You can make it by electric and magnetic fields that vary in time, change in time. Those are all the only ways we can create electric and magnetic fields. If you supplement these ideas about how you make and change electric and magnetic fields with 2 field equations, the fact that the electrical force experienced by a charge in an electrical field is QE, and that the magnetic force experienced by a moving charge in a magnetic field is QVB. These 2 forces together determine the combined electromagnetic force on a charge. So this then becomes the complete theory of how you generate electric and magnetic fields, how you create electric and magnetic fields, and the resulting forces that charges experience in electric and magnetic fields. So this is the complete electromagnetic theory. Okay, I'm getting overly excited about that because I got it in one slide. Let's move on with the most remarkable, amazing prediction that came out of Maxwell's electromagnetic theory. That's the prediction of an electromagnetic wave that he identified with light. So these bullets here are intended to give you a non-mathematical idea of how electromagnetic theory, from the last slide, predicts the existence of electromagnetic waves that we will recognize that light, visible light, say, is an example of an electromagnetic wave. So you can create electromagnetic waves by taking a charge, supposing I had a little charge here, and I oscillated left and right, or vibrate it left and right. That will create an electromagnetic wave. Supposing I add an electrical current here, and represented by this finger, flowing to the left, and I oscillate the direction of the current. It flows to the left, flows to the right, flows to the left, flows to the right. That would generate electromagnetic wave. That's a remarkable thing. You just got to take a charge and vibrate it a little bit. Take a current and vibrate it a little bit. And you'd create bundles of electromagnetic fields, electromagnetic waves that flow off into space surrounding the oscillating charge and the oscillating current. Let's see how it works in a little bit more detail. Let's start with the example of the charge. I'm going to take a charge, here it is, and I'm going to move it left and right, and I'm telling you that that's creating an electromagnetic wave that is propagating through this room and out the doors and into space. The charge, the oscillating charge, obviously, if I take a charge and I move it left and right, that's creating a time-varying electrical field. You can imagine those field lines that sprout out of the charge. I'm moving them left and right. I'm moving that arrangement of electrical field lines left and right. So I'm creating a time-varying electrical field. A time-varying electrical field, according to Maxwell's theory, creates a magnetic field. So this time-varying electrical field is going to also create a magnetic field, which actually itself is time-varying. It too is changing in time. So from moving the charge, we created a time-varying electrical field, and then we created a time-varying magnetic field through what we would call induction, through the connection between electric and magnetic fields. The fact that a changing electrical magnetic field creates a corresponding magnetic or electrical field. So now we created a time-varying electrical field with the moving charge. That's created a magnetic field. That magnetic field is also changing in time, so it's going to create an electrical field again. And that time-varying electrical field is then going to create a magnetic field, and that time-varying magnetic field is going to create another electrical field, and you've got a whole chain. You've got a whole chain, a whole sequence of electric fields creating magnetic fields creating electrical fields, and so on and so forth. They sustain themselves. They keep themselves going in this bundle, this propagating bundle that we call an electromagnetic wave. So this is how you make an electromagnetic wave. And that just streams off away from the oscillating, moving charge, vibrating charge, into outer space. It streams off in the form of bundles of electric and magnetic fields. It streams off carrying energy and momentum away from the moving charge. And that's what we think of as an electromagnetic wave. The same thing would happen if instead of starting with a moving charge, moving it left and right, we started with a current and we directed it left and right. We oscillated a current. So that would also create this chain, this sequence of time-varying electric and magnetic fields that propagate out into space. So that's what an electromagnetic wave is. I'm going to show you a picture of an electromagnetic wave, and I'll show you shortly. I'll show you a demonstration. But I just want to say that when Maxwell worked out this theory, he predicted the existence of this wave, and he was able to predict the speed of the wave. And that was very interesting that he could predict how fast the wave would travel, because it was known at that time, this is more than 150 years ago, how fast light travels. And like he's sitting there, and suddenly you realize that the speed of his electromagnetic waves from his new electromagnetic theory exactly matched the measured speed of light. So there's that moment, right? He realized, he discovered what light is. And so that was a big, big event. Big for him, big for us, I guess. Okay. This is an electromagnetic wave well, obviously it's not a real, this is an animation of an electromagnetic wave. There's positive and negative charge in this source of electromagnetic waves. And so I've got a positive and negative charge in my left and right hands, and I'm oscillating them to and fro, up and down like this. So I'm just moving them backwards and forwards, upstairs and downstairs like this. That's moving charges, and that's creating time-varying electrical field that creates a time-varying magnetic field that creates a time-varying electrical field, and so on and so forth. We got an electromagnetic wave. What you're seeing, well, you're seeing the positive and negative charges. You see them blink on and off here. You're seeing, these are the electrical field lines. So there's electric and magnetic fields that propagate outwards, that flow outwards, but they're just plotting, to keep things simple, the electrical fields. And so these are the field lines that are kind of attached to the original charges, but as the charges move, they kind of are released off into outer space and flow away, carrying energy and momentum. And so that's what an electromagnetic wave, for example, a light wave, looks like when you produce it by varying charges, moving charges, or varying currents, changing the directions of currents. Okay. Error. Well, that's very nice that somebody sat at their desk, James Clerk Maxwell, and mathematically, theoretically, joined together an electricity and magnetism, predicted an electromagnetic wave with a certain speed. But is it correct? Is it correct? Well, obviously, to prove the theory, to establish the theory, you have to go in the laboratory, and you have to measure electromagnetic waves. You have to generate electromagnetic waves. You have to detect the electromagnetic waves to establish the theory, to verify the theory is correct. Heinrich Hertz was the first person to, in the lab, generate electromagnetic waves and detect those electromagnetic waves. He made a electromagnetic waves transmitter, basically. Your phone is one. And he made a electromagnetic wave receiver. Your phone is also one of those. He was the first person to transmit and receive electromagnetic waves. And very interestingly, he did it with a simple electrical circuit that vibrates electric and magnetic, vibrates charges or currents, oscillates charges and currents that are made out of two electrical circuit components that we've talked a lot about, capacitors and inductors. So if you put a circuit together involving capacitors and inductors, you can make what's called an oscillator, electrical oscillator, and it will oscillate electrical charges, electrical currents on and off the plates of the capacitor, for example. So you can build a charge oscillator with an inductor and a capacitor, and that's what he did. He oscillated the charges and the currents on and off the plates of a capacitor very fast. He did it very, very fast. He did it at a frequency that is 90 million cycles a second, 90 megahertz in his units, and that was enough to generate electromagnetic waves that he could detect in his lab. You'll be pleased to know we have his apparatus in this room right now, and we're going to demonstrate it. So here is the electromagnetic wave generator, the electromagnetic wave transmitter. It's this little device here. It's basically a device that has a capacitor and a resistor, and it's going to oscillate currents to and fro, oscillate charges on and off the plates of the capacitor. And it's going to do it very fast at 90 million cycles a second, 90 megahertz. So we're going to switch this on, and we're going to start transmitting throughout the room electromagnetic waves. And they're going to flow from the front of the room all the way back and out the doors and so forth. We've got a detector of electromagnetic waves. It's just actually a copper strip, a long copper strip here, immersed in the electromagnetic wave. This conductor, this copper strip, will experience the electrical field in the electromagnetic wave. Currents will flow. EMFs are generated in the conductor due to the electric field in the electromagnetic wave. And cleverly, we put these little light bulbs on here. And if there are currents flowing in the copper, if there's EMFs in the copper, we'll see these light bulbs light up, detecting the electromagnetic wave. So this is the receiver for the electromagnetic wave. So this is think of this as an early iPhone, right? Here it is, the transmitter in the iPhone, and here it is, the receiver in the iPhone. I'm going to turn out the lights for this. I'll turn this thing on. Like any piece of electronics from 150 years ago, it's going to start glowing. And so here you see it operating. I'm going to turn the lights off. It is generating electromagnetic waves. So you can't see the charges oscillating to and fro at 90 megahertz, but charges are oscillating to and fro at 90 megahertz, and electromagnetic waves are propagating off to the back of the room through you. I'm going to bring up the receiver, and hopefully you can see the little light bulbs are lighting. The little light bulbs are being lit. This is obviously not physically connected to the transmitter. The receiver is obviously not physically connected to the transmitter, but the electromagnetic wave and the electric field in the electromagnetic wave is creating currents and voltages in the receiver and lighting the lamps in the receiver. That's a good one. And this is literally the first experiment that was done to detect man-made, human-made, electromagnetic waves. It was due to Heinrich Hertz, very famous for it, super famous for it in physics. Everybody knows his name in physics. And he's so famous, they call the frequency of electromagnetic waves, or any waves now, Hertz. Okay. Just set the mood again. And get back to the slides. This is just to show you in a little bit more detail. I wanted to put something in the slides that showed a little bit more detail of what was going on in that experiment. As I mentioned, if you walk around this slide, we've got a transmitter, it's here, that causes charges to oscillate to and fro, capacitors to charge and discharge, and I lied when I said it was 90 megahertz, it's 85 megahertz apparently. So these are the charges appearing on these two antennae changing backwards and forwards at 85 megahertz. Those changing charges and currents create time-varying electromagnetic fields that then they themselves create time-varying electromagnetic fields, and that's the reason the bundle of electromagnetic fields propagate out through space, carrying energy and momentum. Then we used a receiver, this third bullet here, we immerse that in that electromagnetic field, and the electric field in the electromagnetic wave cause the charges, induced charges to flow, currents to flow in the receiver. That lit the light bulbs in the receiver. So I want to having discovered electromagnetic waves, turn to properties of electromagnetic waves. This is going to seem like a bit of a laundry list. Each slide is a new property, an important property of electromagnetic waves. I want to get through the properties and then we'll look at a few illustrations, examples of these properties. We said the electromagnetic wave is built out of electric and magnetic fields, and there's some interesting relationships between the electric and magnetic fields in the electromagnetic wave. The first important relationship I want to describe is that the electric field, so that has a direction, the magnetic field, that also has a direction, and the motion of the wave, that has a third direction. All those directions of the electrical field, we denote that E, the magnetic field by B, the motion, the direction of motion, the speed of the wave, we conventionally denote that by C. No idea why, but we conventionally denote the speed of the light wave by C. All those three directions are mutually perpendicular, mutually at right angles to one another. So the electric field and the magnetic field in electromagnetic wave are at right angles to one another. You actually saw it in my pictures of induction, where a electric field induced a magnetic field, or a magnetic field induced a magnetic field. When I drew those pictures of electric and magnetic fields, field lines like this, inducing loops of magnetic field or electric field like that, the induced electric and magnetic fields were at right angles to the inducing electric and magnetic fields. So it's built into Faraday's law that the electric and magnetic fields in an electromagnetic wave will be at right angles to one another. They're also at right angles to the motion of the wave. And we call that type of wave where what's waving is at right angles to the movement of the wave. We call that a transverse wave. Transverse wave means whatever's waving, in this case electric and magnetic fields, is waving at right angles transverse to the direction of motion of the wave. So if the wave, in this picture, like the wave is traveling roughly from the left to the right of the room, the electric and magnetic fields will be vibrating up and down or away from you and towards you, this direction. So right angles to the motion. So that's an important property of an electromagnetic wave. That's not going to work. Oh, I must have jumped somebody. Yeah. Not only are the directions of the electric and magnetic field related, and related to the direction of the electromagnetic wave, but the sizes of the electric and magnetic fields are related to one another, and the speed of the electromagnetic wave. So there's a second sort of relationship now between the sizes of E, B, and C, like there was a relationship between the directions of E, B, and C. And I've listed it on this slide here. The ratio of the electric field to the magnetic field. So the ratio of the newtons per coulomb of electric field, the teslas of magnetic field, is equal to the speed of light. Speed of light. This is 3 times 10 to the meters per second. We'll mention that more on the next slide. But the ratio of the two field strengths is equal to the speed at which the wave travels at. So again, that comes out of the induction, the nature of induction, the electric and magnetic fields in induction. Well, the sizes of them, of the induced field and the one that's causing the induction, they're related to one another, obviously, and that relationship predicts the fact that the ratio of the two fields equals the speed of the wave. So that's the second important relation. And then this is the key thing that Maxwell was able to figure out. The speed of the wave itself is actually determined by 2 constants of nature. The constant of nature that we associated with electricity, So we called it the Coulomb constant K. Sometimes we called it the electric permittivity epsilon naught. This equation is easier to write in terms of epsilon naught, so I'm using that here. So that was a constant describing we started off with it describing just how strong or weak electricity happened to be as a force. There was a similar constant in the world of magnetism. Right? There was a constant in the world of magnetism that we called the magnetic permeability. We gave it the symbol mu naught, and it described just how strong or weak the magnetic force happened to be. At that stage, epsilon naught, mu naught were just two constants that describe the strength of these two forces. But now we see in this slide that their product, if you take the product of those two constants, you take its square root and you take the inverse of that, that's actually the speed of the electromagnetic wave. So the speed of the electromagnetic wave is predicted by the electric permeability of free space, the magnetic permeability of free space. The electric permeability and the magnetic permeability were known to Maxwell, so Maxwell was able to predict the speed of his electromagnetic wave. This is how he recognized that speed that he predicted for electromagnetic waves corresponded to the speed of light, the speed of sunlight or any other form of light. So that was the basis for this great prediction and this great discovery that light is actually an electromagnetic wave. This is personally, there's a lot of formulas in physics, and some of them are careful, some of them I don't. But this one I think is a really nice formula. I'm very fond of this formula, how it connects, because to me it represents this grand unification of electricity and magnetism and light. They're all joined together now in electromagnetic theory, and this is kind of the emblem for that connection of magnetism, electricity, and light, because it involves the three constants that describe those three worlds. The constant describing electricity, epsilon naught, the constant describing magnetism, mu naught, and the constant describing light, the speed at which light travels. They're all connected in a relatively simple way in this formula. So you gotta like it. Okay. Next few slides are about an important characteristic of light. It's an important property of light. That is, this property of light is the reason we're alive, the reason for life on Earth. It's that light actually carries energy and momentum. So it's the energy and momentum, it's the energy that the light carries from the sun to Earth that keeps us alive and everything alive on Earth. Without that energy, there'd be no energy arriving at Earth, no energy to sustain lives. So this feature is very important. When you talk about energy and momentum carried by light, a wave, the language we use for the energy and momentum carried by light, a wave, is a little bit different from the language we would use for energy carried by, say, a particle, like a billiard ball, or like an electron or a proton. When you think about energy and momentum carried by a particle, we tend to think in terms of the individual energy, the individual momentum that particular particle owns. So I might be imagining an electron, and I would say how much energy that one electron carries, how much momentum that one electron carries. That's not very useful. That's not very helpful way of thinking about things when you think about a light wave. Because a light wave is not a little packet. It's not like a particle, an electron or a proton. It's a smooth, streaming wave, a smooth, continuous wave. So how are we going to talk about the energy that's carried by a light wave when it's smooth and streaming? How are we going to talk about the momentum carried by a light wave since it's smooth and streaming. It seems much harder than for a particle where it's discrete and concrete, and we can say how much energy that particle has, how much momentum that particle has. What we do is introduce, we're going to introduce two new quantities. They're called intensity and radiation pressure. But basically what they describe is the energy flow that's carried by a light wave. So energy flows with the light wave as it spreads out throughout the room, and we're going to describe that energy flow. Momentum is carried by the light wave, and we're going to describe that momentum flow. So when we describe energy momentum for waves, like light waves, we tend to describe the flow of the energy, the flow of momentum. We're going to use terms, intensity, radiation pressure, that help us describe the energy flow, momentum flow, rather than the energy and momentum of a particular particle like an electron or a proton. That's the plan. Okay, this slide is about energy and about energy flow in an electromagnetic wave. It's about that quantity intensity, given the symbol I, that we use to describe the energy flow in an electromagnetic wave. So let me introduce this. I've got 3 bullets here. Firstly, you all know that light carries energy. You all know that, for example, sunlight carries energy. Anybody that's been a sunbather knows that sunlight carries energy to you. It warms you up. So that is energy. That's the energy carried. That's the flow of energy in light, in sunlight, for example. We measure that flow of energy as the is the average rate of energy flow per unit area, and we measure it in watts per square meter. So the way to think about that is, imagine some surface. Imagine some surface. Imagine the light passing through that surface. The number of joules that light carries through that surface per second for each unit of time, per square meter, per unit of area, that's the intensity. So that's how we measure the energy flow, is the number of joules of energy per second, per square meter, through some surface that we're thinking of, that we're picturing, visualizing. So that's energy flow. That's what we mean by intensity. Since it's the energy per unit of time, per unit of area, it's measured in joules, that's the units of energy, per second, that's the unit of time, per square meter, that's the units of area. So intensity is joules per second per square meter, or more compactly, intensity is watts, which is joules per second per square meter. So these are the units of intensity, and it's measuring energy flow. Here's 2 key equations, 2 related equations really. That intensity, I, the energy flow of an electromagnetic wave, is not unsurprisingly, right, related to the electric and magnetic fields in the electric and magnetic wave. So the stronger the fields, the larger the intensity, the more energy flow there is. The weaker the fields, the smaller the intensity, the less energy flow there is. And those 2 equations describe precisely the relationship between the electric fields and the magnetic fields in the electromagnetic wave, and the intensity flow, the intensity of the electromagnetic wave. So let's just walk through them quickly. Intensity I, if you write it in terms of the electrical field, is given by this little equation here. It's 1/2 times the square of the field. But remember, the field is varying. It's oscillating up and down. And so that E is actually E subscript M for E subscript maximum. That EM is the maximum electrical field. It's the amplitude of the electrical field. So the equation says that the intensity is 1/2 times the square of the maximum electromagnetic field in your electromagnetic wave, divided by this product of constants that we keep meeting in today's class. Mu naught, magnetic permeability, and c, the speed of light. It's not surprising to see these because this is an electromagnetic effect. And so we see constants associated with electricity, magnetism, and light. And so 1/2 Em squared divided by the product of mu naught and c. That's one way of writing the intensity in terms of the electrical field. You can also write it in terms of the magnetic field. Look, the electrical magnetic field, we said we're related to one another. The maximum electric field is related to the maximum magnetic field. So they're connected to one another. So you can also write the equation in terms of the maximum magnetic field. And this is the second equation here is that version. It's again 1/2 times the square of the maximum magnetic field now, but the combination of constants is different. It's molar plus 1/2 Bm squared times c over mu naught, not divided by c times mu naught. So it's just a manipulation of the constants. And so either of these can be handy. If you know the electrical field, you want the intensity, well, you'd use the former. If you know the magnetic field, you want the intensity, you know the latter. If you know the intensity and you want the electrical field, you use the former. If you know the intensity and you want the latter, you use the second equation. So they're both handy. What about the radiation pressure? What I call the radiation pressure. This is a measure of, it's a funny name, but light does exert a pressure. Like I can exert a pressure on the desk, and I'm exerting a pressure on the floor. You're exerting a pressure on your chair. Light can exert a pressure. If it was shining on the chair, it exerts a pressure on the chair. If it's shining on the desk, it exerts a pressure on the desk. If it's shining on the floor, it exerts a pressure on the floor. Now, the pressure of light on the floor, or on the desk, or the chair is not very big. It's very, very tiny, very hard to measure. But light does, when it shines on something, exert a pressure. So I had said that every sunbather knows that light carries energy, because you can experience it. You can feel it. It warms you up. Not every sunbather, I venture, most sunbathers don't know that light carries momentum, it exerts a force. But light carries momentum, it exerts a force. We characterize the force that light exerts. Again, like we talked about flow of energy through a surface, we tend to think about the force of light over a surface. Force divided by a surface area, that's pressure. That's why we talk about radiation pressure as being the way that we characterize the force of light. This is an effect that is very, very, very tiny. And so it's very, very hard to establish, verify. And it wasn't till decades after Maxwell's theory, wasn't until after Maxwell was dead that it was verified that light actually exerts forces. But light does exert forces. The radiation pressure, so that's the newtons per square meter, is related to the intensity, that's the joules per second per square meter, or watts per square meter, by these two equations. What's a little bit funny here is that I'm giving two equations for the radiation pressure, because I'm giving two equations for the radiation pressure because there's two extremes of light striking a surface. When light strikes a surface, right, with a bathroom mirror, it reflects back off. It's 100% reflected, essentially. When light strikes a wall that's painted black, none of the light is reflected, it's all absorbed. And so there's kind of two extremes, two regimes of light striking a surface, where that light gets reflected, like a mirrored surface, like the bathroom mirror, where it's all reflected off, or where light strikes a surface which doesn't reflect light, like a black painted wall. that won't reflect the light. So there's two extremes, and for those two extremes, there's two relationships, two corresponding relationships between the radiation pressure, that's on the left-hand side here, and the intensity, that's on the right-hand side. If the light's all absorbed, you just absorb all the energy, then the radiation pressure is the intensity divided by the speed of light. If the light is reflected, the radiation pressure is twice as big. It's twice the intensity divided by the speed of light. Why is that? Think of it, think about throwing a lump of clay at a wall versus throwing a tennis ball at a wall. If you throw the lump of clay at the wall, it carries some momentum, it's absorbed by the wall. It sticks to the wall. So you transferred that momentum. You've exerted a force that corresponds to that transfer of momentum. When you throw the tennis ball at the wall, it bounces back at you. When you throw the tennis ball at the wall, it carries some momentum to the wall, and its momentum is reversed. So the wall has actually absorbed twice as much momentum to conserve momentum. The same thing from light. We're throwing light at a wall that absorbs it, it absorbs that momentum. When we throw light at a wall that reflects it, it has to absorb twice the momentum. So there's twice as much force for light that's reflected as there is for light that is absorbed, and these two equations represent the two extremes. Let me demonstrate. I think I'm going to show a video for this one because, this is, if you're at the back, you've got no chance with seeing, absolutely zero chance of seeing this demonstration. This demonstration, which is down here, you can take a look at it at the end if you like, just has a desk lamp as a source of light, which we now understand is carrying energy and momentum, and can transfer energy and transfer momentum, exert forces. It's going to shine light on, we've got a beautiful glass sphere. It's almost evacuated, not quite evacuated. It contains what looks like a weather vane. So you can see it in this picture here. I got a different lamp in this picture. This is the desk lamp. This is the glass sphere. And here in white and black, you see the veins of this kind of weather vane-like thing. And it can rotate on its axis. Okay, so I'm pointing at it, like down here. And here's the lamp. And then I'm going to switch the lamp on. And right now the vane is stationary. As I switch the lamp on, wow, it starts to turn and rotate and get faster and faster. How could that possibly be that it starts moving? The only way it could be moving is that there's some forces acting on it. There's some energy transferred to it, and it's the energy and the momentum that's transferred to it via the light wave. And so I turn the light off there, and I don't know what, I'm going to turn it on again. Just to demonstrate, it's so amazing to see just light exert this force, transfer this energy and momentum, and rotate this weather vane. It would be fine if the wind was blowing the weather vane around, but now the light is blowing the weather vane around. And so that's the energy and momentum in an electromagnetic wave. Okay. So we've discussed the fact that light is an electromagnetic wave. It's a bundle of oscillating electric and magnetic fields. And we've looked at the properties of the electromagnetic fields and the speed of the wave. We've looked at the fact that the light wave carries energy and carries momentum, transmits energy and momentum through space. light waves in Maxwell's electromagnetic theory, light waves are characterized by a frequency and a wavelength. So the wavelength of a light wave, or any wave, is the distance in space, number of meters in space, between successive crests of whatever's waving in the wave. In this case, it's the electric field and the magnetic field are waving in the wave. So it's the distance, the wavelength is distance between crests of electric field or crests of magnetic field, or troughs of electric field, troughs of magnetic field. So that's the wavelength of an electromagnetic wave. The electromagnetic wave, or any wave, also has a frequency, or a period. So the period of an electromagnetic wave, or any wave, is the length in time, the duration in time between successive crests or troughs of whatever's waving, in this case the electric and magnetic field. So a light wave is also characterized by its frequency. That's the time between successive crests of the electrical field, or the period is the time between successive crests of the electric field or successive crests of the magnetic field. The frequency is just the number of crests of electrical field per second, or the number of crests of magnetic field per second. So we characterize this or that electromagnetic wave by their frequency and their wavelength. Now, a couple of important things. One is that electromagnetic waves, the frequency, so that's the symbol F here, measured in hertz or inverse seconds. The wavelength, that's the symbol lambda here, measured in meters. They are related, the product of them is equal to the speed of the light wave. So if you're thinking about electromagnetic wave, you can't just think about electromagnetic wave with any old random combination of wavelength and frequency, because the product of the wavelength and frequency is determined by the fact it's an electromagnetic wave and is equal to the speed of the electromagnetic wave, the speed of light. So that's an important constraint on the possible frequencies and wavelengths of electromagnetic waves. So that's a constraint on the frequencies of electromagnetic waves and the wavelengths of electromagnetic waves. But other than that, Maxwell's theory says that there's a whole spectrum, it's called Maxwell's rainbow, a whole spectrum, a whole range of different wavelengths of electromagnetic waves and different corresponding frequencies of electromagnetic waves. And this slide is a picture of that spectrum. This is a graphic of that spectrum of electromagnetic waves, or this Maxwell's rainbow. So let's take a look at the chart over here on the left. There's two axes that I've labeled on the chart. One is frequency in hertz, and one is wavelength, for example in meters or millimeters or whatever, some units of length. So those are the two axes. If you say you've got a wave of a certain wavelength, 1 centimeter, that determines the frequency. It's about 10 to the 11 hertz. If you said you had a wavelength of 1 nanometer, that determines the frequency. It's about 10 to the 18 hertz. That's because the product of those two things, the wavelength, which is the right-hand axis, the frequency, which is the left-hand axis, that product must equal the speed of light. So once you determine the wavelength, your frequency is fixed. Or once you determine the frequency, your wavelength is fixed. But other than that, there's this whole spectrum, this whole world of frequencies that are predicted to exist by electromagnetic theory. From low frequencies, that's the bottom here, to high frequencies, that's upstairs here. Likewise, there's this whole spectrum of wavelengths of electromagnetic waves that are predicted to exist. From very long wavelengths, look, there's a kilometer down here, to very short wavelengths up here. This is a picometer up here. So Maxwell's theory, when it predicted electromagnetic waves, predicted a whole enormous spectrum of electromagnetic waves. Now, at the time, well, we knew of visible light. That's how we interact. One of the ways we interact with our surrounding world is because we detect visible light. But visible light is the tiniest slice of the electromagnetic spectrum. Visible light is some tiny ribbon of electromagnetic spectrum. Here it is, and it's greatly exaggerated here, and even more exaggerated here, of wavelengths from about 400 nanometers. That's the shortest wavelength. That's kind of blue-colored light, violet-colored light, to 700 nanometers. That's the longest wavelength. That's kind of red-colored light, orangey red-colored light. So that's the visible spectrum. And our whole world, our whole lives are based on sort of interacting with that tiny slice of the electromagnetic spectrum. Now, at the time of Maxwell, it was known that there were other waves. There was what was known as infrared. Infrared radiation is also electromagnetic radiation. It's just a bit longer wavelength than visible light. And so infrared was also explained by electromagnetic theory. Ultraviolet radiation. You can't see ultraviolet radiation like you can't see infrared, but you can feel infrared, and you can, when you get sunburnt, experience ultraviolet. Ultraviolet was also explained as an electromagnetic wave. It's just an electromagnetic wave that has a bit shorter wavelength than visible light. But beyond infrared, which is, as you see here, is longer wavelengths than the visible spectrum, and beyond beyond ultraviolet, which is the other side, a shorter wavelength from visible light, is further spectrums, unknown worlds, completely unknown worlds of electromagnetic radiation, completely unknown at the time, right? At longer frequencies are X-rays and gamma rays, right? And so X-rays and gamma rays are enormously important in medicine, and those parts of the spectrum were unknown at the time of Maxwell's, but have become known since the time of Maxwell because of his prediction of electromagnetic waves, and we put them to work. We put X-rays to work, we put gamma rays to work. Downstairs here, at longer wavelengths, is there anything possibly interesting at longer wavelengths? Well, there is. There's microwaves. That's how I cook every day. And there's radio waves. That's the way that our cell phones work, transmitting and receiving waves from towers. So we've put these waves downstairs here to you. So this moment in time when we went from, we just interact with the visible light, 400 nanometers to 700 nanometers, and maybe we feel warm because of infrared, and maybe I got sunburnt because of the ultraviolet. We've expanded our interaction artificially by learning about X-rays and gamma rays and using them for good, learning about microwaves and radio waves and using that for good. We've expanded our world of electromagnetic radiations. It's really a really huge consequence, a huge technological consequence of electromagnetic theory that is hard even for me to understate. Okay, let's do a quiz. I'm going to give you almost no time to do this because I am so panicked about at least getting one example done that we'll move almost straight on. This is a question. This is a question about what does doubling the electric field in an electromagnetic wave, what does it do to the magnetic field? Does it change it? What does it do to the intensity? What does it do to the speed of the electromagnetic wave? It's a question about all those features we've just been talking about of electromagnetic waves. Okay, so I'm going to jump in. It does not change the speed of the electromagnetic wave. All electromagnetic waves, no matter how strong or weak their fields are, no matter how short or long their wavelengths, or how high or low their frequencies, they all travel in vacuum at least the speed of light. So it's not going to change the speed of the electromagnetic wave. It doesn't double the intensity. So if you remember, the intensity does depend on the electric and magnetic fields, but if you remember back to those two formulas on one overhead, the intensity goes as the square of the electric field and magnetic field. So if you double electrical magnetic fields, you're going to quadruple the intensity of the electromagnetic wave. The thing that it does double is the magnetic field. So if you remember another slide, the ratio of the electric and magnetic fields is a constant. It's the speed of the wave. So if you double the electrical field, you have to double the magnetic field to maintain that constant. And that is dictated by the law of induction. Okay. I've got 3 examples at the end of this lecture that obviously I can't go through. I would take a look at them. They're rather straightforward applications, right, of what we've done over the past 20, 30 minutes. One's about the relationship between the intensity of a wave and its electric and magnetic fields. It's using these 2 equations that I described earlier. Another one is about the intensity of the electromagnetic wave and how it's related to the power of the source of electromagnetic waves, for example, a light bulb. Let me just say a few words about this one, because it's an important example. Imagine you've got a perfect light bulb. By perfect light bulb, 100% efficient light bulb, I mean it's a 40-watt light bulb that emits 40 watts of light. Now, no real 40-watt light bulb emits 40 watts of light, but we've got a perfect imaginary one that emits 40 watts of light. What does it mean to say the light bulb emits 40 watts of light? It means that every second it emits 40 joules of energy. So there's 40 joules of energy per second being radiated by the light bulb. Imagine surrounding the light bulb with a 1 meter diameter sphere. So here this is to help you picture it. That 1 meter sphere, every second 40 joules of energy goes through that 1 meter sphere. That light, as it emerges from the light bulb, we don't lose any energy. We don't create any energy. It just, that energy carried by the light just flows outward. So through a 1 meter sphere surrounding the light bulb is 40 watts or 40 joules per second. Through a 2 meter sphere, now imagine a 2 meter sphere, this big, surrounding the light bulb, twice the radius. Through that 2 meter sphere, again, you're not going to destroy or lose or create any energy. So 40 watts or 40 joules a second flows through that 2 meter sphere. So this question is about what is the intensity at the radius of 1 meter, what is the intensity at the radius of 2 meter. To find the intensity, which is watts per square meter for the 1 meter sphere, you've got to take the 40 joules per second, 40 watts, and divide it by the surface area of the 1 meter sphere. Surface area of a 1 meter sphere is 4 pi times 1 meter squared. 4 pi is 12.6, so it's 12.6 meters squared. That's the area of a 1 meter square. And so if you take 40 joules and divide it by 12.6 meters squared, that's the intensity, and that comes out to be about 4